Hello again, guys. We're going to do deploying deep neural network in a Raspberry Pi, 25 minutes, and test the performance of it. So that's the plan. That's the plan. Let's see how far we get with this thing. I did it in 10 minutes, so hopefully you guys will do it quickly as well. So first, some requirements. I don't know you're connected or you want to do it. You need a laptop with internet connection. And you need a terminal, like an SSH or in Windows, I think it's called now this PowerShell thing, or I lack Windows knowledge anymore. And you can connect using this command here. Select one of those. I was planning to use the first one for myself to present, but if there are more people than the 9 Raspberry Pis available, please share, and happy to share as well myself. So we have 9 Raspberry Pis prepared, 3 Raspberry Pi 3B Plus, 3 Raspberry Pi 4s, and 3 Raspberry Pi 5. And there are different ports, as you can see, and the ports are more or less connected to the number of the Raspberry Pi. I will leave this open for a minute while you guys connect. And yeah, exactly. We will be deploying a very simple AlexNet. Steve is still around. He may complain because it's a very, very old neural network, but it's a good starting point to show how you can deploy things here. So user and password are there. You connect via our public temporarily enabled IP, which is this one starting 193. Yes, so while you connect, I'll explain what we are doing. There is another slide, but I will leave this slide here for now. Assume that we have trained our model with whatever, TensorFlow or PyTorch or whatever tool you want, MATLAB, Caffe, whatever. You train your model, you're happy with it, you have all the data sets validated, fine, fantastic. The last step you do, you export it to a format called ONNX, which is not only a format, it's also a runtime, etc., for an inference engine, but we will use ONNX, as many people are using, as a standard language or file format to represent a network. We're not going to deploy an ONNX. We're going to deploy our own format, but this is not a problem. We have a tool. I won't show it here. So I'm telling things we're not going to see, but it will happen throughout. The ONNX can be converted to Klepsydra's format. It's a binary format that can be loaded very quickly because it's a serialized set of classes. So the loading time is in the order of tens of milliseconds in an embedded computer, which can be interesting for certain type of applications. But the main benefit is it doesn't need any third-party libraries. So the minimal version that I'm going to show you of Klepsydra AI doesn't need any third parties, only a purely C++ 14 library. I know everyone is using Python, Rust, whatever, but no, we are still sticking to good old C++ for now. Okay, everyone connected already? Can I move to the next slide, or you guys need another minute? Okay, I'll assume that we're okay to continue. Yep. Good. So exactly what I was saying. So the AI universe contains several phases: data preparation, training, validation, etc. We're only focused on the last part called deployment. It's the only part that we're going to show here is we have trained our model and we will deploy it to the Raspberry Pi. So how are we going to do this? Sorry, guys, we're not using Red Hat. We're using Ubuntu. I don't know where you guys are anymore, but apt-get is still quite a nice tool for us. So the Raspberry Pi has inside a Docker, and in Docker you will find a container running Klepsydra. No worries if you don't know Docker. It's easy. The commands are coming. The commands are coming, so you can just follow the commands that I'm going to present. This container has also the binaries of Klepsydra and example. It's not compiled. You will compile the example, but the example is already present. So if you guys are there, let's go first to the Docker part. So first, always the commands in yellow. You need to see the image that you have. So you type this command, Docker images, and it will give you theoretically one image, which is the one containing Klepsydra. This is what we release to customers. The Klepsydra AI software is like this. And you copy this value here. I know you can also copy the tag, but in order to save the pain of typos, just copy this number, image ID, and then you type this command. Those who are more expert than me in Docker, feel free to do it whatever manner you want. I just put in the very simple way to do it for the non-initiated. So you run this command, which will do is start a container. The container will start with this, will be created, and you can use it. The container is an instance of the image running on the live on the Raspberry Pi. After you run it, you do the Docker PS. This will give you the list of containers that are running. Again, you copy this ID, not the other one, this new ID in red, and you type this command. Why we're doing this? Because we are going in and out of the container. So in this way, the container is running on the background. It's not killed when you exit. It's a little bit of a session thing. So you run this, assuming that everyone has gotten to this point. I will move to the next slide, unless someone else tells me otherwise. Okay. Good. Now we run this little command to see if Klepsydra is installed here. You can see this. It's not mandatory. It's just to show that Klepsydra is installed. As you can see here, there are a lot of binaries associated to third parties like OpenCV and ONNX. We're not going to use those. We're going to use a minimal version that doesn't require any of this. No. Move on into the next one, so we don't run out of time. And now comes the meat of it. Let's go to the root folder, so the home of root, in the case of this particular instance of Docker. And then we do a copy. We do a recursive copy of the folder with the examples. This comes when you install Klepsydra in your machine under user local sources or whatever you install it, whatever /sources/KPI examples. There are all the examples. You copy all them locally to your root folder, so we can start compiling. And we go to one, sorry, this one is not highlighted in yellow. It should have been. You go to the folder AI min example. So this is the example that is minimal, no third parties. Your binary will use approximately 4 megabytes maximum, so it can be uploaded to space. So if you want to run this in a space and you have the capacity to upload 4 megabytes, you can run Klepsydra there. After that, you do make dir. So we are going to compile C++ as usual. So we go to the folder build, and there you do CMake. CMake is the standard kind of preparation of the make files in C++. Most of you, or some of you, will be familiar. Those who are not using Rust. After that, you will see some output like this, and it should finish correctly. Raise your hand if you face any errors. Hopefully not, because we don't have time to fix them. But yeah, that will be the execution of the CMake command. After that, you just type make, your standard make command. Okay, good. So if everyone is at this point there, actually not doing it. Actually, you can use any Raspberry Pi and just following the scripts. So to be honest, I don't have time to do both things. After that, we will run the example. We will run the example like this, without any arguments, and it will fail because we need to provide some arguments. The arguments that are required are two files that are the two critical files to run any algorithms with Klepsydra. The first is the configuration file. This configuration file contains mostly the optimization details. How do you want to optimize the model, the execution of the model? And the second file is the model itself. As you can see, it's called alexnet.kpsr, not alexnet.onnx. because we're not using RNNX as I told you. The KPSR is a binary format, JSON style, that deserialize into objects what you have been creating. So you run this, and it fails again. And it says that you need a PC signature, which is what we need in order to get produce a license. So we will do another thing, which is this. Hopefully you guys are following. I'm not receiving any feedback from the audience, assuming you guys are doing well. You need to do this export identification strategy to 0. So this tells you that we are going to identify the computer in some way with Klepsydra. You run it again, and then you will get this PC signature. All the Dockers in this particular instance that we prepared have the same signature. That means that you need a license for this. So now we exit the container by typing exit. So this will leave the container running, as I said, but you are back into the Raspberry Pi main prompt. And you will find a file. You can use CAT or BI, whatever is your preferred tool, and you will see that the file has the same license ID as the PC signature. So once you have done this, go to the next step, and then we copy this file from the Raspberry Pi into the Docker container, and you do with this command, where this number here that I have lighted there correspond to the container ID that you did with the Docker PS. So copy this file over there to the root folder, run the Docker exec again, the command, so you are back in the container. And we go again to the folder of the build. We export again the identification because we didn't store it in our bash rc file, and we export also the license file like this. Once you have done this, you run the example again, and now it works. Finally, hopefully for you guys, it's also working. It worked for me when I tested this. Hopefully it's working for you. And important point, if you are in the, well, it depends on the Raspberry Pi you are, because they have different performance, obviously. But in the Raspberry Pi 3B Plus, you will get something around 100 milliseconds, unless most of you are in the same Raspberry Pi 3 and trying at the same time, then the latency will be horrible. But assuming that you are in different ones, it will be in the order of 100 milliseconds for the AlexNet, which is remarkable because if we run it with TensorFlow Lite, you will get at least 200, 250 milliseconds. So this is kind of already you're seeing the benefit of running with Klepsydra. Super briefly, this is how the example looks like for your information. So the API of Klepsydra is quite simple. There are many boilerplate lines about measuring timings, etc. But there are only these few lines. So extension backends is a vector that we need in case you want to provide your own mathematical backend. I won't go into details, but this is something you can do here. Then the instantiation of the actual DNN, where we load the model and the configuration file, like I said. Then go create an instance of such a DNN. We register, and now it comes the real thing. You register a callback, because Klepsydra, as opposed to other inference engine, is asynchronous. So you don't wait, you don't block the system until you get a response. You just have to register a callback, and then you call predict. Predict is a function that actually executes the AI. No? So you have an image from the camera, from the file system, whatever. You do this predict. You get control back immediately, and you get an ID. Sorry, you get an ID, and this ID tells you when the callback is called. You can compare. You can validate with ID if this is the image you were waiting, or a previous one, or a future one, whatever. Now, I will follow. Okay, until we have time. If we don't have time, 5 more minutes. Okay. We may not have time. So the next step is to install BI. I know this brings more I don't know, more conflicts and controversy than the current political environment, if Vim or Emacs or whatever. I'm not going to enter into that detail, so install whatever you want. Even you can use Notepad or whatever it's called now in Windows and then copy the file. But the important thing I wanted to show you is you can collect statistics. So there are a number of properties in this file that help you collect the statistics in two manners. One is, or multiple manners, via sockets for real-time monitoring, and via file if you want to dump it into a file. If you want to do real-time monitoring with sockets, we have a tool also, a plugin to OpenMCT, which is a well-known NASA tool. So you can see this kind of thing here, the CPU, throughput, etc. that is happening even at the layer level. You can see each layer, how much latency is requiring. Or if you configure this for file, it will create a CSV file. You change all these values here. I will leave it here for a second, just in case you want to do it. So you change these three values, statistic enable, container name, and the static file name. You run the example again, and then you will start collecting statistics. And the statistics will look more or less like this. So it's I'm not going to go into details, but it's a breakdown per layer of the latency and the number of execution, the time that the element was enqueued in our ring buffers, etc. All this information is calculated by these statistics. Moving on, only if we have time. What we just run is optimized for latency. So if you look at this file, there are other properties called parallel threads, which is a value of 4, because all the Raspberry Pis we're using have 4 cores. So we are parallelizing, we're using all the parallelization possible here, like this. So we have 1 event loop and 4 parallelization threads. And with this, you usually get the optimal latency for this type of algorithms. If we want to optimize for CPU, we change these properties like this, which I don't think you will have time to do it. But if you change this property to use 4 cores, one parallelization, and you increase the number of threads that the system can create, you will get a much higher latency, in the order of 3 times higher. But the CPU consumption will be very low. We're talking about 1/3 of the CPU that the TensorFlow Lite requires. No, so this is quite powerful. It depends on the application. That shows, no? If you need an application with low latency, you will get a higher CPU, but a very low latency. But if you need a lower power consumption, and you are happy to sacrifice a little bit of latency or a lot of latency, then it can be done in that way. And somewhere there will be a solution that obtains the optimal throughput. But this, you cannot do it by yourself. This has to be done by our tools. And for that, you will need to export a file called the stream configuration. What does this file have? Another JSON file that tells you in which core or which event loop each layer is running. So it shows something like this. By default, it's set one default configuration. But we have a tool that will start playing with this and start changing the distribution, changing the parallelization thread, and seeing how you can obtain the best throughput out of the system. No? So this is how and this tool I'm not showing because it's a little bit long. It takes sometimes takes several minutes to calculate the optimization. It's a visual tool called the SDO, and it will generate a new file of this for you. And this is one of the files that you need to provide as part of your building or execution of the AI. So code-wise, always the same code. You just play around with these configuration files. And if you're using Artems, another operating system, it works in the same manner. It just instead of JSON file, it will be C files. And I think that's it. I don't know how far did you guys get. Hopefully you run something.
Thank you, Pablo. The slides are up. People can go offline and follow the instruction. It's very detailed. Thank you. My question would be, how long would it be up and available for folks to try it online?
I can leave it until the end of this week. The DevOps told me not to leave it for too long.
All right.
So maybe until end of this week, you guys have time to play around with this thing.
All right,
If
that's
someone
great.
is really interested, let me know, and also we can share a trial with you guys.
Okay, thank you.
Thank
I
you.
have a question. We can take a question. There is one online. It says, thanks for the demo. The usage seems pretty straightforward. You mentioned that a custom backend can be provided. Would this be the suggested approach to support, for example, new models like YOLO V7, or could existing kernels code generator be used as a starting point?
That's a very good point. I mean, yes, this definitely can be used to develop your own layers that are not supported currently in Klepsydra, but we're always adding new layers. So at some point, the YOLO V7 layers, we know that they have a few new layers. It will be added, it will be absorbed into Klepsydra. But exactly, this is one of the main capabilities of this extensibility guide.
Very good, thank you. Any questions? There's a question here.
I had a quick question regarding, I guess, how CPUs are used with your tool. So I was wondering, does it require the entire CPU, like entire core, to run the neural network, or can I run something else in that core as well while it's doing your neural network stuff? Like, would it be able to, like, if the core is needed to run some other component in my flight software, can I pause what your tool is doing, run my stuff, and then unpause? And
Yeah,
continue?
that's a very good point. I mean, sharing the same core is difficult, but it's possible if there is some kind of hypervisor sharing the tasks. Yes, in that case, it's possible. But what we usually tend to do is reserve only a number of cores for this. Instead of using all 4 cores, we say, okay, we just dedicate 2 cores for this and the other 2 cores for other activities. And everything works the same. You optimize for the rest of the available cores.
Gotcha. Thank you.
Thank you, Pablo.
Thank you very much, guys.